the beers also? I knew that. Who was giving that one? Yeah, I did that one if I could.
But at least, yeah.
Okay, guys, shaken not stirred lab this week. Yeah? The one on the original syllabus, we're back on the regular schedule. Good morning to you all. We need to pass back a polarimetry sheet from the Thursday lab only. If you want to pick it up here, please yell. Lauren Wheeler.
Here.
Stephen Hutto. Here. Kendra Williams.
Here.
Sobathita. Steve Houston. Here. Tia Banks.
Here.
Sanjana.
Here.
Allison Lewis.
Here.
Lauren Ingalls. Michael Sadamka. Here. Sinead.
Here.
Rachna.
Here.
Karan. Here. Sarah Rosenberg.
Here.
Ty Templeton. Here. Simone. Michael Aldridge. Rabia.
Here.
Aja. Acevedo. Ria.
Here.
Michael Wilson. Here. Troy. Sarah Ryan. Tiffany.
Here. Sarah, you're not in Thursday lab. No. Well, technically, I am.
Okay, guys. Nucleophilic substitution.
This is definitely not my favorite.
I think that's her favorite.
We looked at two different mechanisms. We had a model reaction. Ultimately, we decided which mechanism the model reaction was. Let's move ahead. Kinetics studies have shown that the rate of the above model reaction can be affected by changing the concentration of either the alkyl bromide or the hydroxide. Either one. This indicates that the rate depends on both of them. Because the rate depends on both of them, each must be involved in the rate determining step. And the reaction is thus bimolecular. The rate depends on both. We also know that the rate is first order with respect to each substrate. Thus the rate equation is second order overall and is written as follows. K is some type of constant times the concentration of both substrates. Because it said both up here. Question. Which mechanism matches these observations? SN1 or SN2? SN2. SN2 is bimolecular, right? Yes. We've already answered which mechanism. The SN2 mechanism is described here. It has a rate, some type of constant, times concentration of both substrates. We've already done a reaction coordinate diagram for each. What is the rate equation for the other mechanism? The other mechanism is SN1. What's the rate equation for that?
Is it just K times the 1?
K times concentration of what? Yes, that's it. Only that. The hydroxide is not involved in the rate determining step of the SN1. The rate is thus not dependent on the hydroxide. The rate is only dependent on the alkyl bromide. SN1, right? Let's look at another reaction. Here's a reaction in which we have another alkyl bromide, a little bit different here. This is a secondary bromide, secondary halide, KOH. We can do a substitution reaction. Hydroxide can replace or substitute the Br, and we can make KBr. Very similar to before. In this example, this reaction is known to give complete inversion. That is, if we start with R, we now have S, and S only. This reaction is thus an antioselective. It only gives one enantiomer. This is the first antioselective reaction we've ever seen. But the only reason it's antioselective is because we started with a single enantiomer. But the important thing is we get inversion. Inversion of stereochemistry. Questions about this? First off, what is the mechanism? There's only two substitution mechanisms here, SN1 and SN2. Is an SN1 mechanism more or less likely for this reaction compared to the previous model reaction?
More likely.
Why is it more likely?
Because it's already secondary?
What do you mean it's already secondary? You mean it is secondary?
Yeah,
And the previous one was
primary.
primary. And an SN1 mechanism involves forming what type of intermediate?
Primary.
Carbocation. So the previous one would have been a primary carbocation, and this one would be a
Secondary.
secondary. Okay, so let's ask the question again. Is an SN1 mechanism more or less likely for this reaction compared to the previous one?
Less likely. Less likely. More likely.
No, it's more likely. So this one would involve forming a secondary carbocation. The previous one involved forming a primary. Which one is easier and thus more likely? Secondary. Which mechanism, SN1 or SN2, does the stereochemical outcome support in this reaction here? Inversion. SN1 or SN2? You guys reviewed the previous page over the weekend? And looked ahead at these questions because they were coming today? Good. So which mechanism did you say the stereochemical outcome supports? If it was SN1, we'd be making a carbocation.
Yeah.
How do you take a carbocation in terms of stereochemistry? Either side. Okay? If this was SN1, we would ionize, make carbocations, and then hydroxide would attack either side. We should get racemic. We only get inversion. Inversion supports SN2. Mechanism for this reaction, hydroxide. These electrons, okay? The bromine is projected back. How does the nucleophile come in? I can't show it on the board, but it's coming in from the front. Kicking this off. That's a concerted SN2 substitution mechanism. And the new bond to the OH should now be forward, correct? Yeah? So we have SN2 backside attack. if this is the outcome of the reaction, the mechanism must be SN2. Even though SN1 is more likely than the model reaction on the previous page. Let's look a little bit closer at this inversion. How is inversion obtained? 5-coordinate transition state. Okay, I'm going to redraw the compound. Starting material R there. Let's see if we can do it here. I have the bromine this way. There's the ethyl. That's H. And this should be R. H is forward. We've got bromine, ethyl, methyl, so we're going counterclockwise when H is forward, so we reverse it clockwise. R. It's the same compound, just drawn a little bit differently. Hydroxide attacks this carbon, which we have some partial plus. I'm going to kick it out. Okay. Which way is it going to attack from? The bromine is that way. Which way does hydroxide come? Hydroxide comes in direct opposite, called backside, or opposite. The bromine is that way in the plane of the board. This comes in 180 degrees opposite. So it comes in over here. Now it has to sort of come in between these. These two are really eclipsing each other. If you had a model, they're really like this. This comes in here. I'm going to kick that off. But what does the transition state look like? Any reaction has a transition state. It's partially between the two. Let's see if we can draw it over here. I'll draw in the carbon. Okay? We're basically doing this, but the transition state. In the transition state, this bond is breaking. So it's kind of like this. This bond here is forming. Sort of like this. The three groups here on that carbon, other than the bromine, become planar. Now, these two are going to have to eclipse. These two are right in front of each other, eclipsing. Okay? One's forward and one's back like this. Okay? And then the ethyl is straight up. Ethyl straight up. One's forward, one's back, coming up the other thing. Okay? And then you got this coming in. Charges. This thing is negative. Once the hydroxide fully bonds, the oxygen becomes neutral. So what's between negative and neutral?
Partial negative.
Partial negative. This is neutral, but once it leaves, it becomes minus. What's in between neutral and minus?
Partial negative.
Partial minus. This is transition state. Sometimes they're put in brackets. Sometimes you'll see like a double dagger. That looks like a pound sign. Something like that. I don't see it too often. maybe it's something a little bit different, but usually indicates transition state. Importantly, what's the geometry of the three things here on the carbon, other than those things? One thing straight up, and then one forward, one back coming down. If I turn this like this, boom, boom, boom. Okay? Can you imagine if I just took this and turned it like that, 90 degrees? That would be coming forward, and this would be going back. Okay? That's planar. What does this look like? Trigonal planar. These three things are trigonal planar here. It's just the plane is this way. Okay? I've just taken it and turned it here. Bond angles are 120 degrees. Is the bond angle between the H and methyl is 120 degrees. The bond angle between the ethyl and the H is 120 degrees. Again, because that H is really coming forward, right? That thing's straight up. That's 120 degrees. If it was like that, that would be 90. Boom, boom. But the H is also a little bit down. It's 120 in the back. And then between here and the methyl going back, that's 120. Okay, if I could just bring it out, the methyl's going back, but that's 120 degree bond angle there. Okay, it's 120 all the way around. What does this look like? Trigonal planar. Again, if we ignore this, what's the geometry here of everything? Or what are the bond angles here? Between the H and the methyl?
109.
109.5. Yes, tetrahedral. This is trigonal planar, 120 degrees. Okay. This is an sp2 like transition state. An sp2 atom has 3 hybrids. What's left over after the 3 hybrids? P orbital, right? And it would be perpendicular to that trigonal planar. If we draw that P orbital here, it's kind of like that. This is kind of like a P orbital here. sp2-like transition state. 120 degree bond angles. How do we get the end product? This bond completely forms. This bond completely breaks. And as this completely forms, these 3 things move that way. Let's draw it. We'll have a hydroxide. Here's the carbon. Now we have an ethyl. We have an H, and we have a methyl. Plus what? Plus Br minus. These electrons completely break away as this more forms. Transition state. This is R. What is this over here?
S.
That's S. We have inversion. Inversion comes from backside attack. It goes to an sp2-like transition state. Inversion, inverted. It's almost like that term comes from umbrella. Here's this compound here. These 3 things are sort of projected that way. bromine blue. We'll put three things on there. Bromine blue coming straight this way in the plane. The other three things are going, if I make the ethyl, let's make the ethyl black. It's going up and then there's one more. But those three things are really kind of going that way. You see that? Where does hydroxide come in? It comes in from over there, directly opposite of the bromine blue. It comes in here. As it comes in, what does it make these three things do? The existing three things? It makes them flatten up. I can't do this. It makes them flatten. I'm going to break it. Okay? You see? Now it's planar. You see the plane? Okay? Plane is here. It's like a piece of paper. Flatten them up on that paper. Now the hydroxide is partially bonding, and there's your sp2-like transition state. Now what happens? It kicks this completely off. But these three things go from here. See, I can't invert this. As it completely makes, then they push to the other side. Ooh, okay. Now we have the OH coming here and it's back to tetrahedral. All right? So it's kind of like an umbrella being inverted in the wind. You've ever seen that? If you think about it, if the umbrella inverts, it goes through a planar transition state because it's sort of that way. It has to go planar before it goes the other way. You guys get, you guys always want to think that the H is folded, inversion means it's dashed. No. Not here. Okay. Questions about the transition state? We'll see some applications below with this. The transition state requirement. What's the requirements for the transition state? Are there requirements here? Yes, the requirements is it must go from 109.5 to 120. That's a requirement. It's not like, well, I may do this or I may not. No, this is it. It has to do this if you're going to do an SN2. Can this requirement affect reaction rates?
Dr. Stevens,
Uh-huh.
is this the same page that we printed out? Because we're missing like number 4.
Yeah, got that.
Oh, you don't have this?
It goes on to E.
We have 1 through 3 and then it goes to E.
We could draw it in on the back side. Give us
Okay.
a second.
I'll have to see if you're missing anything else. We'll have to get you, I may bring a fresh copy on Wednesday. I may have sent you an old PDF. Okay, look at these reaction rates. You react this guy, got a leaving group, both of these have leaving groups. With potassium iodide, I-, right? This is organic chemistry. Get rid of your spectator ions, right? Right? Did you learn that? Spectator ions, get rid of them, right? All they do is just watch what's going on, right? They don't do anything, so ignore them, right? I-, I-. I- can replace the Br in a SN2 reaction here. Rates. If this rate is 1, this rate is much less than 1. Why is this reaction so much slower?
Because of the three-membered rings, stability.
Do what?
Three-membered ring has lower stability.
Why would that make the reaction slower?
That would probably make it faster than let's say. Let's see.
Bond angle here is 60 degrees, 9th grade geometry. Bond angle here is greater than 60 degrees. This is the one we want to explain. Why is it slower? Right there it's 60 degrees. What bond angle must that achieve in the transition state for this SN2?
109. So, 120, I'm sorry.
120.
Yeah.
Is this going to be able to go to 120 pretty easily? I'm stuck at 60. I've got to go to 120. Whew. Lots of stretching needed to go there, yeah? That's why it's so much slower. The transition state, which must be achieved, is much more difficult for this, and you may think even impossible. Apparently it does react a little bit, but it's way darn slow. Got to achieve the transition state. E, reactivity of various electrophiles in the SN2 reaction. The effect of a p orbital being immediately adjacent to the reaction site. All of these guys here are very reactive in an SN2. These here are all much more reactive than this guy in an SN2 reaction. Because there's a p orbital next door. Let's just take hydroxide. These electrons attack here and kick this off. At this carbon, what type of geometry does that carbon take on in the transition state? sp2-like. With a p orbital, sort of. The bonding is sort of like in a p orbital. Okay, I erased it, right? The hydroxide is bonding. The leaving group is leaving. You already have it drawn here. Let's go back and look at it. Okay? P orbital-like it becomes in the transition state. What if we put a p orbital next door? What can happen here?
Because conjugated?
Conjugation. And what is conjugation? It's a stabilizing effect. If you have conjugation going on in your transition state, that's going to stabilize the transition state. Make it easier to achieve. P orbital next door to the carbon where the reaction is taking place. Do you have a p orbital next door? Yes. Do you have a p orbital next door? Yes. Do you have a p orbital next door? Do you have a p orbital next door? You actually have two, although only one can be conjugated. Because of the p orbital next door stabilizing the transition state, these react pretty darn quickly in SN2. Do you have a p orbital next door here?
No.
No. You don't have any stabilization. All these guys tend to be very toxic because they react very easily with nucleophiles in your body, in your eyes, anywhere, liver. Very easy SN2. You ever watch baseball and, I mean, this here is just one carbon less. Ethyl chloride. Official name would be like chloroethane, but it goes by ethyl chloride. You ever see baseball players foul a baseball off like their ankle and they're like, trainer comes out and sprays some stuff on the ankle? It's a numbing spray. It makes it cold. Okay? It's ethyl chloride. It's compressed, and when you spray it, it volatilizes, and that requires heat, so it removes heat from the surroundings, and if you remove heat from the surroundings, you become cold. It's also used in some dermatology applications. You want to numb the area or something. Okay? Not that toxic. Okay? We'll learn more about the ability of this to be a leading group, not that toxic. These you would never spray on somebody unless you wanted to do some ill. These will cause your eyes to start watering and going, okay, toxic, cancer causing. You'll have to evacuate the stadium. Okay, here. Much more reactive. Why? I've already explained why. Okay, what are we doing? We're looking at reactivity of various electrophiles. What is the electrophile? The electrophile is the species with the leading group, right? The nucleophile is the thing with the electrons, like the anion. We've got a partial plus here. So electrons are attracted to it. It likes electrons. It's an electrophile. Okay, we're looking at it. Here's one thing to look at. Now let's look at the effect of carbon substitution. Rates. Methyl bromide is very reactive in an SN2 as an electrophile. It's more reactive than this. Primary halide. The halide's on the primary carbon. Secondary halide. Tertiary halide. Bromine on tertiary carbon. The rate gets slower. This is faster than this is faster than this, and this is way faster than that. Why is this fastest? Let's draw those H's in. Yeah, they're kind of small, right? Here comes your nucleophile. Bam. Take that off. What if we instead make these H's other groups? Maybe like methyl groups. Now this carbon's tertiary. Now how are we going to get in there? Oh, I got it. There we go. It's going to be slower. Okay? The more substitution you have on this carbon, the more sterically hindered it becomes. Okay? It's sterics. I mean, look, this is wide open. Attack here, bam. Attack here. Well, again, it looks like you can get in there, but remember, there's H's there as well. And it's starting to get a little congested. And it's starting to get more congested, yeah? It's like, hold on, forget about it. You know, I'm not even going to go there. Steric hindrance is detrimental to an SN2 reaction. Least sterically hindered for backside attack. Very fast also, kind of. They're getting slower but doable. Bam! Never do SN2 with tertiary halide. Too slow. Just doesn't happen. All right? Take home for us. Never do SN2s. Too sterically hindered. Now, the above trend is just the opposite for an SN1 reaction. But you already knew that, right? Which one's going to react fastest in SN1? Well, according to the statement, this one. Why is this fastest in SN1? Because SN1 involves forming carbocation. That's going to be the easiest to form carbocation, right? That's reasonable. Would you ever form a primary carbocation? And certainly never this. The trend is just the opposite for SN1. Here's some actual rate data. Replacing the BR with iodide. The same type of compounds. Fast, a little bit slower. Slower. We'll do a secondary. It's not the greatest, but we'll do it. Tertiary, never do it. It's not going to give you a reaction. Trip to the dentist? Do y'all have trip to the dentist? Okay, we're looking at the idea of steric hindrance at the reaction site. Okay, really going to slow down in SN2. Anybody eat pre-dental? Okay. We'll look at the chemistry of the anesthetics that are used in dentistry. Okay. Some are short-acting, maybe last about 10 or 15 minutes to a quick procedure. Some are longer-acting, maybe last several hours, half a day. Okay. All the anesthetics are, the length depends on how fast they're degraded in the body, how fast the drug is degraded. If it's degraded quickly, it'll be a short-acting anesthetic. Okay? They're degraded by a reaction we haven't seen, but it's also influenced by sterics. More sterics, the slower it's going to be degraded, the longer the drug will last. Okay? If you look at some of these, like lidocaine and a titocaine, I believe a titocaine is a longer-acting anesthetic. If you look at the structure around the ester group, it's much more sterically hindered. And so the body takes longer to metabolize it, so it lasts longer. Okay? So that's largely based on sterics, affecting the rate of the hydrolysis reaction. The chemistry, you'll see in organic 2. If you want to see these types of anesthetics, you can look them up on Wikipedia, like dental anesthetics, you'll get a page. Okay, that was looking a little bit at the carbon with the leaving group. Let's look at leaving group ability. Let's focus in on that thing. In the examples up there, for example, they were all bromine. We've already said that iodine's your best leaving group, better than bromine. Typically, you never see F as a leaving group in this class. All right, iodine's best, etc. Here's an example showing this. We take this substrate with this nucleophile, all right, O negative, right? O negative. We're looking at the oxygen coming in and kicking off the iodine. We make this bond here, we make potassium iodide. It's pretty easy with iodide. Try to do the same reaction with the alkyl fluoride. Very difficult to impossible. It's just not going to react. Thus, we say that F is a lousy leaving group. It doesn't want to leave. And indeed it is. It's pretty lousy. It's actually much worse than chlorine. Okay?
That's for both SN1 and SN2?
Yeah, we can also apply this to SN1. Yeah. A lot of these things will apply to SN1 as well. In fact, everything applies to SN1 unless we say it doesn't. I mean, everything is sort of universal here. We saw trends. We pointed out that the trend's actually opposite with SN1, which makes sense if you know that forming the carbocation is a rate-determining step. Okay, so there are your halogens. Pretty straightforward. Iodine's best. Now in terms of which one's commonly used, probably the bromine is most commonly used. You might say, well, why don't you just use the best? Well, iodine compounds tend to be a little bit unstable. Because if you look at the decomposition of them, the decomposition is actually favored. If you do some calculations. So they tend to decompose. Bromine compounds are more stable. Now, on industry, they tend to use the chloro compounds. You might say, well, why? That's going to be a more difficult reaction. You can do it. Why don't they use bromo? Well, because chloro compounds tend to be cheaper. Chlorine is just more common. So in industry, the cost is more a bigger factor. On research scale, bromine's your best. Because it's cheap enough to easily buy, and it's also good reactivity. All right. What about other atoms? Can other atoms be leaving group? What about oxygen? Oxygen is not a good leaving group on its own, by itself. Okay? For example, look at this. If we do the same reaction up here, if you want to take the methoxide and try to replace the hydroxide, kick it off and make this bond and make hydroxide, it's not going to react. Terrible leaving group. Will not leave. Okay? Will not act as a leaving group in a slow rate determining step. Now, why do I clarify slow rate determining step? In this mechanism I'm showing SN2, this is the slow rate determining step right here. Yeah? Okay? It won't leave. Hydroxide will leave in a fast step though. Okay? But not in the slow step. We can do this reaction though. If we do it this way down here, it will work. And down here, we're going to protonate the OH first. Okay? In the first step down here, we have an acid catalyst. And these electrons can react with the H+, and that will give boom, 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 oxygen. And we have protonated the alcohol. Now we have a good LG. Neutral oxygen, not good. A positive oxygen will serve as a leaving group. Now we can come in here with the nucleophile. And these electrons come in here, kick off the positive oxygen. And a concerted SN2. That gives what? Oxygen with a methyl, an H, plus what? Plus water. Essentially what's serving as your leaving group is water. Okay? And we just made this bond. We didn't magically lose the H. How do we go from here to here? Well, you just give back the catalyst. There's got to be a minus here. What's your favorite strong acid? This is strong acid. Okay? Strong acid. What's your favorite strong acid?
Sulfuric acid.
Okay, that means we would have HSO4 minus as the counteranion. And this could take the H. These electrons stay behind. That would give that product plus what? We'd reform our catalyst. this would be overall called an SN2 reaction, most likely. But there's actually 3 steps here. The first step is, how do you want to describe it? What do we do in the first step? We protonated the oxygen. What else? How else would you describe this? We activated the leaving group. Okay? Leaving group activation by protonating it. That's a step. Now, is it a substitution? No. It's sort of just a preliminary activation step. Here's your SN2. Right there. Nucleophile, backside attack, kickoff, leaving group. That gives this. We got to get rid of the H, and that's the third step. Okay? So, you cannot do it up here, but we can do it with the acid catalyst. Now, if you note in the previous reaction, we used methanol. We used H plus and methanol. Why did we not use H plus and methoxide? Why not do the reaction like this?
Because then it wouldn't just make methyl.
What?
Or would it just, is that,
They would
if the
react.
methoxide would react with the catalyst before it would react
Yes.
with anything else?
Yes. You cannot have a strong base and acid in the same reaction. Okay? These are not compatible. You cannot have acid and base in the same reaction. All right? Those will just react together. So in the previous reaction that worked, we used the neutral form of that nucleophile, methanol. Methanol can exist with strong acid. Okay? Now, this brings us to the next reaction. A common reaction you see is reaction of alcohols with HX to make alkyl halides to give water, plus water. Mechanism for this reaction. This is a strong acid, all right? We can protonate the OH. I'm just going to protonate it. We've already showed the mechanism for protonating an OH. We will protonate an OH 1,000 times this week. I'm not going to show every time I protonate. All right? This mechanism was shown on the previous. Okay. But once we get it protonated, we also have I minus. Right? I minus come in, kick off the water, which is a good leaving group if we can, yeah? What does this give? We're done. That's it. It gives the I on the carbon and you kick off water. Common reaction of reacting alcohols with like HBr, etc. And so here's your SN2. Can you predict the products here? In addition to OH groups being leaving groups, OR groups can also leave, if you can make the oxygen positive.
The hydrogen's gonna attach to the oxygen and then make that positive, and then those are gonna leave. The BR.
Why don't you predict product of that reaction?
Ethanol.
We'll look at it on Wednesday. We probably all need to look at mass spec on Wednesday. You get back to mass spec some. Okay. Then we'll be moving on to B, another way to make OH a good leaving group. Have a good